The mountain car problem is a problem where a car has to move up a hill but don't have sufficient power to manage by its engine alone. Thus the car has to use the momentum of the slope behind it to get up the hill in front. This is achieved by wiggling back and forth. The car has three options at any point in time: gas, reverse, and do nothing. The problem is solved once the car reaches the top of the hill. We also try to minimize the time it takes for the car to reach the top. We used an actor-critic SARSA system with Q-learning with the same core algorithm as the one in Project 1. This animation shows the relationship between the actor and the critic, and the order of the arrows illustrates the flow of the algorithm. The algorithm starts by taking action A in state S, moving into state S' and receiving reward R. Then the actor chooses a new action A' based on S'. And the critic calculates the TD error based on the reward. Then the algorithm loops through all states in the current episode and uses the discounted TD error to update the actor's policy table, as well as to update the gradient and weights of the neural net in the critic. This project is quite different from Project 2. For one, Project 2 was an adversarial game where we trained a neural actor using the Monte Carlo tree search. In this project, however, we trained the critic using mostly the same techniques as in Project 1. However, some differences in the game creates the need for different strategies. One difference is that Peg Solitaire has illegal moves in some states. This is not a limitation, however, but rather simplifies the sim world of the mountain car problem, which does not have illegal moves. The mountain car problem has the possibility of going on forever, and thus a max number of turns might need to be set. The mountain car problem also has an infinite state space, because the states are continuous variables. This means that some different strategies have to be used for the actor and critic to recognize similar states. For this, we use coarse coding. The state of the mountain car problem consists of two continuous variables: position and velocity. As mentioned, this makes for an infinite state space. Since the actor uses the policy table to choose an appropriate action, there has to be a finite number of possible states. It is also preferable to use discrete values as an input for the neural net in the critic to make the predictions for state values. A solution to this is to encode the state into a discrete form by using coarse coding. This can be accomplished by overlaying a number of grids over the two-dimensional states and offset the grids differently in all directions, as illustrated in the animation. For each time step, the continuous point is translated into coordinates for each grid overlay. The grid coordinates are then translated into indices for each grid. The resulting output can be used as an input for the neural net in the critic and as a key for the actor in the policy table. A difficult part of solving the mountain car problem is to reach the goal for the first time during training. The car is very unlikely to reach the goal by selecting random action at each time step. Thus, the model struggles to learn. It never completes the task within the 1000 time step limit. We realized that a more consistent approach was to use the car's velocity as a variable in the reward function. As a result, the agent would continuously learn to favor high velocity, which is necessary to reach the top of the slope. We also found that using eligibility traces in both the actor and the critic provides good results. The graph describes the decreased amount of time steps needed to solve the problem in the later episodes. The following graph illustrates the learning progress of a model which converges upon a solution to the problem. The x-axis represents the best position the car encountered during the episode. We see that the modified reward function helps the car gradually reach higher up on the slope, even though it has not yet reached the goal position. When the car reaches the goal for the first couple of times, it quickly learns how to solve the problem consistently. For this run, we used a high epsilon value in the early episodes and gradually transitioned into exploiting what the agent had learned so far. We can see that the agent consistently solved the problem using an epsilon greedy strategy in the later episodes.
Here is a high-level overview over our code structure.